Okay, good morning, everybody, again. Thanks for being there. We will continue our discussion on waves. And before I start, I would like you to ask, if you want, any questions that you might have about yesterday's, Monday's lecture that I gave. Excuse me. Yeah, you don't. If you don't have any questions, that's absolutely great. So today I left you on Monday with one. We were discussing a particularly complicated topic, I would say, which is diffraction. And excuse me. And I briefly mentioned Young's experiment. Maybe I have not yet given a perfect definition of diffraction. Diffraction is hard to define. It is really a combination of phenomena, but perhaps I was thinking one good way to define diffraction is that diffraction is essentially the ensemble of phenomena that where you clearly see a failure of, if you think in terms of optics, of the corpuscular theory of light. Or in other words, diffraction is what we observe every time that the propagation of waves cannot just be described in terms of a simple ray path, one ray path going from each source to each receiver. So we have, every time you have something that some authors would call secondary source, that is some sort of obstacle that scatters a wave field around. Okay, so diffraction is basically a concept that goes hand in hand with the Huygens principle, the Huygens idea of what a wave is. In Huygens' view, in fact, every little parcel of matter is an obstacle that scatters the wave around. Every time a parcel of matter, whether it be a rock or a gas or some kind of fluid, every time a parcel of matter receives a wave, it becomes itself a source and it diffuses the wave around. Okay, that's what Huygens postulated. And Fresnel improved this idea by introducing the concept of interference. So this is a very subtle thing to think about. In seismology, I and my colleague often make this mistake, in a sense I just did, to say that this obstacle scatters the wave around, in reality, what happens is that if the matter is not uniform, if you have irregularities, then neighboring object will diffuses the wave in different ways. Depending on the properties of matter, some materials might be completely opaque, so they won't diffuse the wave at all because they're not able to respond to it. They're not able to, they won't move, okay? Think of a wave that propagates in water. When it hits a rock, there's not enough energy, there's not enough coupling between water and rock to move the rock around unless the wave is very big and the rock is light or small. So when you have this sort of irregularities, then interference starts to play an important role. Well, interference always plays an important role, but that's when we actually can observe it. To better explain what I'm trying to say, let's think of some practical example. So I'm switching, as I anticipated last time, I'm going to be switching a little bit between optics and acoustics and seismics, because in many ways, the fundamental phenomena that we observe in these three domains are the same, and also because the way the physics of wave has developed historically has been through a combination of these disciplines. And in fact, originally, most of the concepts that we now use in seismology were developed in the field of optics. Fresnel, you know, now if you do seismology, you will hear this name more and more, was actually someone who never really worried about acoustic or seismic waves. He was a physicist of optics. He was a student of optics. So now think of light coming into your room, and think of some obstacle, okay, that like a wall. What happens when a plane wave of light, so light coming from far away, coming from the sun, hits this obstacle, is that the obstacle casts a shadow. Okay, so this part of the room will be dark. But if you like, depending on the size of the obstacle and of the size of the opening, people like Fresnel, like Young that I mentioned, and Fresnel observed that the difference, the distinction between shadowed area and illuminated area is not so sharp. And in fact, light does propagate also into the dark area.
But
yes.
So here it depends on the index of refraction of this matter.
Say that again.
It depends on the way where the light is coming. If it is coming straight, and if it's coming like this, so it depends. The propagation
yes.
will depend on index of refraction when he hit the wall or no.
So in the experiment that I'm going to tell you about, basically, it's I want to go. Let's let me take it in a different way. We basically here we have only two indexes of we have only two media, either vacuum or air, and something that is completely opaque, an obstacle.
Okay.
So I'm not talking yet about refraction or reflection or whatever. I guess really what I want to say, I really shouldn't spend too much time yet on diffraction, but basically what I want to say is that if you have light coming, there's no angle. So we make a really simple experience. Okay, we have
with no angle. With no angle.
No, not necessary for what I want to for what I want to mention. I really want to touch, like these are very complex concepts. I just want to touch briefly on them, just so that you're aware of them, and then we go back to the basics. But you're right to ask questions. So please, if something is not clear, that was a good point, continue to stop me.
Okay.
If the point is that if array paths, if just thinking in terms of array paths or of all particles, just think of a wave that is something that resembles the propagation of matter, even if we don't know that that's not exactly what it is, then you will trace a straight line. This area is illuminated. This area is illuminated, dark, dark, dark. Okay, so maybe you could expect, okay, in optics, I remember what I was telling you last time, that people like Newton thought what our eyes perceive is some kind of molecules, some kind of particles that come out of a light source and eventually hit our eyes. If that's the case, like if matter is just traveling in a straight line, if it hits an obstacle, it bounces back. If it finds no obstacle, it should go ahead. So we should, on a screen that's placed out here, we would observe a very simple pattern of light and darkness, like a barcode, But we'll not forget the barcode. It's simpler than that. Just one illuminated area every time you have a slit, an opening in the screen. Now, what happened in the beginning of the 19th century is that people started to make experiments with very small openings, very small slits, and they realized that what you observe is a much more complex pattern of ray and light, of darkness and light that you would observe in the simple hypothesis, okay, in the corpuscular hypothesis. So what happens, the explanation that people like Young, okay, so this is called the Young's experiment, okay, that people like Young and Fresnel came up with is that you can explain mathematically this pattern if you think that each of these slits becomes source itself of light. Okay, it's a final proof that Huygens principles make sense, and that the idea that light is corpuscular doesn't really work in practice. It also means and that's particularly important for us, that the ray path description of the propagation of waves is not a very, it's not a sufficient description, in the sense that here you have a ray path, okay? One ray path, one individual ray path that hits the end of this opening, but corresponding to this ray path outside of the opening, on the other side, you have an infinity of ray paths forming a circular wave that propagates in all direction on the outer side of this region here. So why does this explanation, like how did Fresnel and Young come up with this idea? What you see here is a very old picture from Young himself, 1807. And what you see here are crests. So these A and B are the two slits that I'm talking about. And the dark line represents the crests of these light waves. Young figured at the time, this was kind of a very courageous way to look at things. But he thought, if light really is a wave, then it will have crests and trough. Now, if I think of light as a periodic wave, okay, as a sinusoidal wave, then the crests would look like this, like in this drawing, okay, a circular wave with simple sinusoidal behavior in time and space. Then what happens is that the crests of the wave, the circular wave that comes out of A, will interfere constructively with the crests of the wave that comes out from B, and they will interfere destructively with the crests, with the troughs of the same wave that comes out at B. So that, if you consider that, you can actually draw a diffraction pattern, as we now call it, that would basically fit the data that you have here. So I don't really, this is not an optics course, and I don't want to get into like advanced optics, but I wanted to mention these phenomena as part of my introduction to waves, because we will eventually, they like, when you use waves for practical purposes, like imaging, for example, like tomography, these phenomena cannot possibly be neglected. Do you have some questions about this?
So if we can summarize,
yeah,
diffraction is that when the light or the wave come and hit the wall, and it's scattering in different in different way.
Yeah, like the keyword for a seismologist, usually the word that is used is scatter.
Okay.
So if a medium is uniform, there's no scatter. Like if you have a plane wave or a circular wave in a uniform medium, it stays circular, it will stay plane.
Okay.
Why? Well, I don't know if I should get into that. There is actually scattering, in the sense that every particle of matter does scatter wave around. Huygens' principle is basically true, we think. But interference is such that everything cancels out except for the plane wave.
Okay.
If you introduce an irregularity, then interference becomes a mess, and you start seeing strange things going on. Young's experiment is just one example. I mentioned it because it's a classic example that if you Google it, you're going to find 3 million explanations much better than mine, probably, and a lot of videos and stuff like that. And it's kind of interesting. It has implications that go into quantum physics. I mean, one could do a whole course on this, basically, seriously. But for a seismology course, that your colleagues summarize it pretty well. Like, we want to understand that matter by its nature does scatter a wave around. Normally, not normally, but in a uniform medium, interference also comes into play and basically cancels out most of the scattering effects. But when you have irregularities, when you have what we call a heterogeneity in the medium, then those interference together with the Huygens effect, with the Huygens principle, gives rise to some complex patterns. So in basic seismics and seismology courses, you probably have heard already about reflection from an interface. So that's a very simple form of scattering. We don't even really call it scattering because it's very regular. It boils down to just a reflected wave.
Yeah.
And if the input, the wave that comes in is a plane wave, the reflected wave is a plane wave itself. And then you will have on the other side, you might have a refracted wave if the reflecting medium also is able to absorb some energy. All of this is explained in terms of Huygens-Fresnel principle. It's all an effect of each particle of matter being a secondary source of wave. If we have time, I will try to do it later in the course in a more quantitative matter. But of course, like if the medium is simple, remember the question that your other colleague asked last time, the solution, like we can find easy analytical solutions if we have simple media. So usually we stick to simple media, but in the most general situation, scattering is really the what we call scattering, or scattering is probably the best term. That really is the one phenomenon that is always taking place. Then if the medium is simple, it also manifests itself in a simpler form. Anything, any other comments that you have? Any other doubt? My next goal would be to start doing a little bit of math, like excuse me. So, if you've seen, some of you might have heard about, you are specializing in geophysics now. Some of you might have taken some courses before. You might have seen a seismic section before. You might have heard of seismic migration. So you might have seen what happens if you start out with a regular seismic section where everything is flat and uniform, very simple layers, blah, blah, blah. And then you see what happens if you put like some sort of intrusion, some sort of, it could be a reservoir, it could be some geological heterogeneity of some kind, some plutonic rock that intrudes sedimentary rocks, whatever, some sort of heterogeneity. Then you have seen that this results in a spherical wave coming off of this intrusion. That's a very simple practical example of diffraction, okay? This intrusion diffracts the wave around, and you will observe it in the seismic section. If you haven't heard of these things, it's not a problem. I'm sure you will get a lot of that in this coming year. So now let's go back to the one question that I really wanted to address before digging deeper into the physics of waves. It's a very basic question. We should all agree when we use the word wave on the concept that we are talking about. So what's a wave? We've given already some definition, but now I want to start to be mathematical, and I want to try to give a mathematical definition. So the one way that I like to define quantitatively, to define rigorously a wave, is as follows. I'm reading it because I want to get it right. So a wave is a phenomenon by virtue of which an observer that's farther down the direction of propagation of the wave will move like a first observer that's closer to the wavefront, provided that we wait during a time proportion to the interval of space between the two observers. So let me make a drawing to basically illustrate what I'm saying. Imagine again that you are on the beach and there's a wave coming in. You see it, so here is you on the beach, and here is your friend who's swimming a few meters, a few tens of meters away from the beach, and here is a big wave coming in. Here I draw the crest of this wave. So what defines this as a wave? As a wave, the idea is that the idea is that if I wait at enough time, and the time that is proportional to the distance between let's call it delta x, and let's call x this coordinate, and let's orient it in the sense of the propagation of the wave. Then if I wait for a time that's proportional to this distance, I will experience the same motion, the same disturbance. That's the word that we used last time, that my friend is about to experience right now. Okay, so the keys are a time that's proportional to the distance. So
we can say that a wave is a disturbance.
We can.
Yeah, I'm asking if we can say that a
Yes.
wave is a disturbance which has in such a time.
Yes. So I guess what do we mean by disturbance? The underlying idea when you say disturbance is that we all have an equilibrium situation that we refer to. So a wave is a disturbance in the sense that it will move me, it will move the observer, it will displace the observer from the position the observer would occupy in the absence of acoustic seismic phenomena in his world or her. So disturbance is just a word like many other words, you know, so you could say a disturbance, you could say a signal, you could call it displacement or a change in velocity. So, but maybe in this particular example, we can keep it simple and just call it a displacement, right? I mean, if the sea is calm and my friend is just floating on his on the surface of the water, and then the wave comes in, it moves him around, and maybe he wakes up. So if no ship passes by, nothing really moves, and there's no disturbance, there's no displacement. So that's the idea. So the key is that there's a disturbance, like that something happens, that there's a displacement that we can observe, and this disturbance propagates with a certain velocity. Okay, so unless there are some heterogeneity in the medium of propagation, in principle, the velocity will stay the same.
Yeah.
And the disturbance will stay the same. So if my friend moves first, it moves up and then moves down, the same thing will happen to me near the shore. Okay, so how do we write it in mathematical symbols? Well, let the disturbance, it could be depending on what my instrument ultimately measure. It can be a change in pressure, it can be a change in velocity, it can be a change in displacement. Let's call it f, a function, and it's a function of x, our spatial coordinates, and time. I call time t as usual. And what my definition says, it says that if I am at a distance delta x from the first observer, sorry, I already, if I wait, let's put it in this way. If I wait a time delta t after the moment the first observer is perturbed by the wave, I will observe the same disturbance that my friend has observed at my position, which is delta x equals v delta t away from the first observers. Okay, or maybe an even better way. I'm going to eventually write the exact same equation. But if I'm positioned at a distance that I call v delta t, because the idea is that there's a proportionality here, okay, as I mentioned, from my friend, from the first observer, I will observe at my position the exact same disturbance that he has observed, only I will have to wait a time delta t. Again, another way to put it, maybe even better, I could go on forever. I'm positioned at x plus delta x, so I will observe a disturbance observed by my friend after a time that's given by delta t over v. You see, even if I haven't said it yet, but what this constant v that I have introduced
velocity
is the speed. Yes.
Speed, velocity, yeah.
V,
velocity.
Yes, very good. Okay. It's velocity or speed or wave speed, whatever you call it. Just as a curiosity, in seismology, we call it velocity. In physics, velocity usually is a vector. So the physicists would call it wave speed, but in seismology, we call it velocity. So anyway, so you understand that V is the ratio of the distance between the two observers to the time that it takes for the signal to travel from the first observer to the second. So it has the meaning of velocity. But remember, it's not the same thing as the velocity of a particle that moves around, okay? It's not a velocity of some mass that moves around. It's a velocity with which the signal, with which the disturbance travel around.
Okay.
The velocity of mass is the velocity with which my friend goes up and down. And it will be in the vertical direction. Well, both horizontal and vertical, right? Because it's a waterway, so it's a bit more complicated than just an acoustic wave, but you don't need to get into that now. So anyway, it's a velocity with which my friend and later myself move around a little bit when the wave comes in. That's not the same thing as V, okay? V in this drawing here, in this diagram here, is the velocity with the signal with which the crest that we see on the water moves.
Yeah.
Okay, so this is very basic stuff that for some of you it might be a bit boring, but it's also easy to get confused about these things. So it's important for me to make sure that we are all more or less on the same wavelength here. Yeah. Okay, so do you want me to repeat something? Did I make sense? Anything that worries you, or should I go ahead?
So, the second equation.
Yeah.
I don't understand that delta T over V, dt over V.
Yeah, so to describe mathematically what a wave is, I'm forced to, I decided to explain it with a sort of thought experiment where we deploy two observers in space, in two different positions in space. They are separated by a distance that I called delta x. Now, the wave is something that travels between the two it hits first the first observer and then it comes to the second. And delta t, I just defined it arbitrarily as the time it takes for the wave to go from the first to the second observer. So after I see my friend moving around because the wave comes in, I look at my watch, and when I am also touched by the wave, that's delta t, right? So these I just defined. Now I said, and that's so that's a definition of wave. So for me to be perturbed by the same disturbance that was first observed by my friend, I have to wait a time that is proportional to the distance, okay? And V is the proportionality factor. So those are all definitions. That's how I decided to define a wave. And then the next step is to say, okay, but wait a second, what does V mean in practice? It's a speed, essentially. It's a speed not of matter, not the speed with which I move, but it's a speed with which the signal, the disturbance travels. Okay, so mass doesn't necessarily move with a velocity v. Plus mass goes back and forth. Okay, when it's hit by a wave, in any case, it always moves first in one direction, then back to the equilibrium position. But the wave does propagate with a velocity v. Okay, so it's we can call it propagation velocity, wave speed, wave velocity. Another question?
Sir.
Yeah.
In the second equation that you wrote, you wrote that delta t over v.
Yeah.
What does it mean physically? What is the? I don't understand. What is the difference between the two equations?
Right. You don't understand it because it's wrong. I'm sorry. Oh, la, la. It's delta x over v. Sorry. Thanks for catching it. Yeah, so I replace delta t here.
Okay.
From this equation, it follows that, yeah. Sorry. But
No problem. No problem.
good that you copied. Okay, anything else?
No, it's all.
Good. Good, thank you. So, yeah, so now, okay, so now now we're going to play a little trick to see there's an interesting property that follows from this definition, and that will bring us to another definition of waves. You know, if you take another course in wave physics, you might, the colleague that gives the course could probably start from the definition that now we are going to get to through some simple or not so simple math. So we according to our definition of wave, a wave is also, and here we have another definition, if you will, a function of space and time, of distance and time, where with this property, okay, with the property that if I wait a time delta t, an observer placed at a distance v delta t from the first observer will observe the exact same disturbance that was first observed at xt. That's another way of phrasing the definition that we have given. Okay, but mathematically, you see, it's not trivial. Okay, this is only some functions, not any possible function f will have this property, right? So from now on, when we think of waves, we know that we have to think of functions that enjoy these properties. And we are going to narrow it down to a very specific type of functions by doing a little bit of math. So what I'm going to do now is a Tailor expansion, which I'm kind of taking for granted, but that you've been exposed to this before. Maybe you haven't, maybe your teachers didn't call it Tailor expansion. I know that if in France, for example, they like it, they call it développement à série limitée. So it's, I don't know how to translate it literally, but basically it's an expansion of a function as a sum of derivatives. What does that mean in practice? It means that I can, if I place myself in the vicinity of a point xt, let's call it in this case, okay, where I know the value of the function, I can make a prediction. If I know the value of the function and of its derivatives in this point, I can make a prediction of what the function will be like, excuse me, of the value of the function at the next location. So, you know, this works well because here I have an expression for the value of the function f at some distance in space and time from some initial position xt. So if I want to, so it's kind of automatic actually to do a Tailor expansion of this guy, provided of course that dt and that both dt and dx are small, which in our case, if dt is small, also delta x has to be small. So notice I'm replacing the big delta with a small delta, because from this point on, I don't want this guy to be large. Okay, I'm going to place the two observers near one another.
Actually, sir, we can say that it's a derivative at any point.
Say that again.
We can say that is a derivative at any point. Simply is change at any location of the given body object. That simply means is a change. It's a derivative.
Yeah, I agree.
And we apply these things Taylor series to find a point at any specific point.
So if I understand your comment, I don't really need to be honest to even speak of Taylor, right? I can just say, I can just use the definition of derivatives. Because you are already guessing that I'm going to stop at first order, right?
Yeah.
If I wanted, I agree. I mean, you're right. I could have, in theory, maybe I was going to go to second order, but obviously it's not going to be very useful for me to go to second order. So yeah, for now, let's forget about the Tailor expansion. And let's just say, well, I don't know, because still it gets a bit complicated because I have two variables that are both changing. So to me, it's kind of, if I just apply the definition of Tailor expansion to first order, what I get
First derivation
is,
yeah.
Just one sec. Let me get my formulas right, otherwise it's going to be yeah, so you see, basically, I guess it doesn't really matter if we call it a Tailor expansion of what or not, but the point is that if if the distance between 2 points is small, the value of a function at the second point is approximately equal to the value of the function at the first point plus its derivative multiplied by the distance. Okay, so you can call it Tailor expansion to first order, or you can call it, like your colleague did, just a consequence of how we define a derivative. I fully agree. If you are not convinced about what I just wrote, you can go back to your undergraduate math and check the keywords are partial derivatives, because the difficulty here is that I'm dealing with two variables, right? So Tailor expansion of more than one derivative, partial derivatives, everything is very closely connected. But intuitively, I hope you find it reasonable that if I multiply a derivative of a function by the increment of the variable, I get basically the difference in the value of the function itself. So that's basically what I'm doing here. But now, this is where it becomes interesting. Look at what I've just written. By my definition of wave, if f is a wave, if f is what we call a wave, then this guy and this guy are the same, right? I've just written it right here, right? So this cancels out, and I'm left with this chunk here that has got to be approximately equal to 0. And since delta x and delta t are as small as I want, we might as well say that this is 0. Okay, as delta t goes to 0. So let's now forget for the time being about how we got here. And what I want to do with you now is to think a little bit about this equation. Okay, I'm going to write it again on the Blackboard. Whiteboard. So what this equation says, it says that the derivative of the function f with respect to space, with respect to distance, is proportional to the derivative with respect to time. And then maybe, you know, this delta t, we can cancel it out. And we are left with this equation. So how in mathematics, like if we forget about the physics for now, and you know, imagine this is a math course, and I'm asking you, what's this? What would be your answer? What kind of equation is that?
It's a differential equation.
Good. That's what I wanted to hear. So this is
differential equation.
So what's a differential equation?
It's an equation that relate a derivative function and another derivative function.
Yes.
Two independent.
That's what I see. That's what I see.
Yeah, of course, your mathematician friend is not to be happy with, but
yeah,
we can accept it as reasonable. But let's state it. I'm going to try to state it in a bit of a more general way. Essentially, a differential equation is an equation, you know, to understand in practice what it is. I mean, I'm sure most of you have seen this before, but you have to think, when you just say an equation in algebra, it's something that relates quantities to one another. Like, you know, the algebraic equation, it's x, I don't know. Let me get an equation of which I can find the solution easily. So this is an algebraic equation, right? X squared plus 4x minus 12 equals 0. And you know that this is easy to solve, right? If x equals 2, you get a solution. And if x, I think 6, could that, yes, minus 6. If x equals minus 6, 36 minus 24 minus 12. So these are solutions, right? So an algebraic equation, when you look for a solution or for some solution of an algebraic equation, you look for numbers, for numerical values that, if plugged into your variable, solve the equality. Okay, so that's an algebraic. A differential equation, in some ways, it kind of looks like it, right? I mean, you have some quantities that sum together, eventually you get 0. But the solution to this guy is not a number, but a set of numbers, if you will, a function. Okay, so, and in general, probably the definition that we should give to be more general about the differential equation, is that it's an equation that involves a function and its derivatives. Okay, and the coefficients also could be functions themselves. That's not the case here, luckily, because for our goals at this point, we can assume it to be constant. Okay, the velocity of propagation, just take a uniform medium or approximately uniform medium, is more or less constant. You can do a lot of acoustics and seismology assuming the velocity of propagation to be constant or approximately constant.
We can also say that this is Abduction equation.
Yes. Equations have names. And it's also called the Abduction equation. But let's not, I don't want to insist too much on this because the physics that strangely enough, that the physics that we're doing here is not, like, the concept of advection probably wouldn't help to understand.
Sir, what I see, tell me if I'm wrong, I see that the derivative of this function by x, it's equivalent of a derivative of this function by time, but we have the v. The v is the k in this difference.
Yeah.
Yeah. Okay. So this is the velocity. Yeah.
The time derivative is proportional to the space derivative. What I would like to ask you next, though, I think I have a feeling, but stop me if I'm wrong, that you basically understand what this is saying.
Yeah.
But now the problem is we want to find a function. So we want to find, and ideally, we could solve it numerically, right? Like I was saying the other day, you can feed this guy to MATLAB or to whatever you like to use, and it's going to give a solution. And in principle, you could stop there and think about something else. But of course, I don't think that's certainly not what I want to achieve in this course. So to gain a deeper understanding of the phenomena that we are dealing with, it's useful to try and find an analytical solution to this equation. So, MATLAB would give you a set of numbers. It would give you an array of numbers where for each value of space, 1, 2, 3, 4 meters, and time, 1, 2, 3, 4 seconds, you get a value of f. And that's what we call a numerical solution. Okay, but in this course, we are not learning to derive numerical solutions that you will do later. In this course, we want to stick to simple problems, but we want to find analytical solutions because we think that helps us to get a better insight in the phenomena we are studying. So how do I get an analytical solution to these problems? And it's not, this is a difficult question. I mean, basically, either you are a bit of a prodigy or you've seen these things before. Otherwise, it would be very hard to answer this question. But if you've seen differential equations before, you might suggest a method. I have one in mind. I don't know if there are others to solve these equations. I guess I have two methods in mind. I'm kind of hoping that you will propose one of them, or neither of them. I'm hoping that whatever you propose is not something that I don't know, but you can try. So if you've seen differential equations before, of the few methods, there's no like recipe to solve a differential equation. Like basically, every differential equation has to be studied per se. There are a few methods that turn out to work in a lot of cases. And for this particular equation, there is one method that people teach in calculus courses that actually works, I think.
So, sir, this is, I think this is a first order differential equation.
This is a first order because we
Yeah.
only have first order derivatives, so it's called a
Yeah.
first order partial differential equation. It's called a partial differential equation because we have partial derivatives. What does it mean, partial derivatives? It means that f is a function of more than one variable, and when we differentiate it, we can differentiate it with respect to either variable. Okay, thanks. But that doesn't solve it.
I don't remember very well, but what I remember that a differential equation for first order, we solve it in two times with a second.
That sounds kind of good, maybe.
When we don't consider the second member, which is called.
I think okay.
I'm talking by a mathematic ways. I don't know if it's.
Before, okay, this is, I'm beginning to be worried because this could go into a lot of mathematics that I'm not that good about. So what I'm going to stop you now, and I tell you that there's at least one easy way to solve this right away, and it's a method. It's a method that's called separation of variables. Separation of variables.
Yeah.
And in wave physics, because the main equations that we deal with can actually be solved with separation of variables. So we'll meet it more than just this time. So we might as well go into that. You understand that what am I doing here? Because I see that that the mathematicians among you participate more than the other. You shouldn't think, oh God, what have I gotten myself into? This is it's not gonna be a math course, but what I'm trying to do now is I'm starting in a sort of not so organized way, but I'm starting a review of some mathematical concepts that we are going to use, okay? But why do I say this? I would like anybody who feels right now that this is a bit confusing or difficult to feel free to stop me and come up with any questions that you might have, okay? So I'm asking questions and I'm happy, or it's helpful to me if some of you answers, but that doesn't mean that you all have to know already about all these concepts that I am throwing at you, okay? The idea is that if you've taken math before, even if you don't remember things, you can go back to your books, to your notes, and do some whatever reviews you need to do.
Yeah.
And if you don't have any books or notes because you haven't taken that much math before, you ask me now, or you send me an email this afternoon, and we'll work that out. Okay. So separation of variables. What does that mean? It means that we make a guess, and like I said, the truth is that unless you're a really especially talented person, unless you've seen this before, like I would never be able to guess it, right? Probably. But since I've seen these things a trillion times, I see this, I say, okay, separation of variables. So let's see if it works. It works. If it works like this. You assume, and it's an hypothesis, you might be right or you might be wrong, but you make the assumption that the solution to this equation can be written as the product of two functions. The first is a function only of space, of distance, and the second is a function only of time. Yeah, you remember now, right?
Yeah.
So now, after you've made this assumption, you plug this expression into your differential equation. And as you will see, that immediately simplifies things. But let's look at it together. Okay, stop me if you have any questions. All I'm doing here, I just substituted equation 2 star into equation star. And this is how equation star looks now. So if I'm right, this will work. And I will be able to find two functions, xi and tau, function of only x and of only t respectively, that satisfy this relationship. So now look at this expression here. Here I have the derivative with respect to x of the product of a function of x and a function of t. The function of t is constant with respect to x, so the derivative doesn't do anything to it. So I can rewrite this thing as tau, I hope you can read well, tau of t multiplied by the second derivative of xi with respect to x. And then I play the same game here, right? So here xi is basically a constant, and then, I mean, it's a constant with respect to t, and then I have the derivative of tau with respect to t. Okay, so now I still have a bit of space here. So now nothing forbids me to divide both terms by the product of tau times t. Okay, so I divide the left-hand side of tau times xi, sorry, by tau times xi, and I divide the right-hand side by tau times xi. The equation is still valid. I'm dividing left and right by the same quantity. But if I do that, and that's the cool part, so here tau cancels out, it simplifies. And here xi cancels out. So I'm left with 1 over xi of x, derivative of xi with respect to x, equals minus 1 over v, 1 over tau, function of t, times the derivative of tau with respect to t. Okay, now I want you to breathe and me too, and think for a second about this equation. This is a funny equation because it says that something that changes only if we change x, if we change the position, has to always coincide with something that changes only with respect to time, that changes only if we change the time. So that means that wherever I position myself in space, if the time is not changing, this guy cannot change. It also means that if I place myself at one position in space, I fix x. I can wait as much time as I want this function here cannot change, because if x is fixed, it can't change. Otherwise, this equation would not be valid anymore, and like everything would fall apart, and the wave couldn't be a wave according to our definition. So if you still agree with my definition of wave, you have to accept that each of these two equations has to be equal to a constant, and of course to the same constant. Otherwise, this equation would not be verified.
Professor, I can see the upper part of the blackboard.
Excuse me?
When you move the camera, I can see the
Ah.
upper part.
Ah,
The over part.
yes,
Yeah.
yes, you're right. Okay. Anything else? All right. So let's call this constant. I don't know, how do we call it? We call it lambda. So we have now two equations. We managed to break it down to two equations. So maybe it doesn't sound that great. I mean, I only had to solve one equation earlier. Now I have to solve two. Is that a good deal? Well, it is a good deal because these two equations are simpler. First of all, they are not partial differential equations anymore because each is an equation that involves only one variable. So you can think of them as what we call ordinary differential equations. And then also, if you look carefully, they are the same equation, right? So if you solve one, you solve the other as well, except that the constant at the right-hand side has changed. So, you know, I could write this, if I multiply both sides by v, I could write this guy like this. And then you see, basically, mathematically it's the same thing, just the constant is lambda in one case and minus v lambda in the other case. So it worked. As I anticipated, that's not a recipe to solve any differential equation. It's one of those tricks that if you know it and if you're lucky, it works in some cases. It works in many cases when you deal with waves. So let's see, let me make some room here. Now,
Sir, what is lambda? What is lambda?
Lambda, we don't know, but it's something that doesn't change. It's a number.
Constant.
It could be anything.
Yeah.
So the way it works in practice is that, like now, I've been doing math and I forgot the physics, but basically, F, remember, is a displacement. Well, it's the displacement. Let's say the vertical displacement. Let's just call it displacement. We haven't been very rigorous in defining the physics of these water waves, but it's the displacement associated with this phenomenon that I have called wave, right? And I haven't made any statement about the medium where this wave propagates, except that the velocity of propagation is constant. It's a uniform medium, and I represent it with this letter v. So in such a situation, what this what the math that I have just done says is that any function f that is equal to a product of a function psi of distance and t and tau of time that are solutions to these these two equations, 1, 2, 1, 2, 1, 2, will be able to exist in our world. Okay, so in principle, it's physically possible to observe any function f that satisfies these conditions, which in turn are connected to these two conditions. So what do I mean by that? To answer your question, lambda could be any numerical values. Things will still work. But it's an interesting question because this is not very useful in the real world, because in the real world, you don't have unlimited media. In the real world, you have boundary conditions, okay? So you never really solve a differential equation by itself. You solve a boundary condition problem. So a differential equation plus, for example, the condition that you don't have an unlimited medium, but you have a sphere with an outer surface that's free of stresses that can move freely. That's the Earth in the first approximation. So when you start placing these constraints, then that will end up restricting things like the value of lambda, for example. We will see that later. Like I anticipate that next week we will do the string, or maybe already on Friday, I have to think about that. So we will solve the, we will discover how a string can vibrate, a string with fixed end. And in this case, the fact that the ends of the string are fixed limit for example, the values that the constants that are involved here can take. Okay, but here we are in an unlimited medium. So basically you have the end result will be that you will have an infinity of possible solution, and every value of lambda can be in principle okay.
Sir, if you don't mind, can I add something?
Yeah.
My brother asked a question about lambda. Lambda is a positive value. We can use only positive value for lambda. There is a three options. Either can lambda is positive, either can lambda is negative, or maybe it's zero. Constant, maybe it's zero. So if this is zero, we are unable to find the non-trivial solution. So
Well,
if lambda is zero, then you only get a trivial solution. We are interested to find the other solution, means non-zero solution. And second thing is that if we use negative value of lambda, it means some restrictions take place in our problem. So we have to restrict something where you can choose just only a positive value of lambda.
yes.
If you solve it analytically, you can find the physics behind this purpose.
Yes. Okay, you're right, but let's get to it step by step.
Okay.
I guess the point that I was trying to make, okay, probably you're right. I forgot lambda has to have either positive or negative sign, probably because we don't want things to explode, basically. Yeah. But let me get to that. In any case, other than that, there's no particular constraint. I mean, we still have an infinity of possible solutions. But you're right. So let's get to that, and that basically anticipates my next question, which is how do we solve? What's a solution to this? To this equation. Okay, now, again, you know, we are faced with an ordinary differential equation of the first order, but we still have to solve it. So again, you know, no recipe to solve a differential equation, but if you've done a little bit of calculus, you probably have the answer if you think about it for a second. What's a function that's proportional to its derivative?
It's an exponential function, no?
Yes, I think
Yeah.
so. I mean, I think so. I know. So I'm sorry. I'm just finding my notes. So excuse me. So it's an exponential function. So if what do we mean by that? It means that if I write that
it's a constant k exponential minus lambda. I think it's if I remember well.
Yeah.
Minus lambda x, yeah. What?
If I take the derivative of this guy, so it's okay, right?
Yeah.
Good. Thanks. No, I mean you're right. So basically, it's another way, like the way what you said is that you more generally you could say that the solution is exponential of kx, and then you discover that k has to coincide with lambda.
Yeah.
To get a solution of this particular equation. So perfectly right. Very good. Thank you. So now, of course, for the other equation, we don't have much more work to do because the only thing that changes is that instead of lambda, we have minus v lambda. So tau has to be the exponential of minus v lambda t. And so let's put these two guys together. And what we get is the exponential of lambda x times the exponential of minus v lambda t. Remember that we are looking for a function that's the product of the two functions. So minus or plus. Well, let's leave it like that. So this brings us to the issue that was raised by your colleague. So actually, I mean, I would say that we were both wrong. I forgot, but it's neither negative nor positive. But if x and t are both unlimited, it's got to be imaginary, right? Otherwise, it will explode either way, I think. Or, yeah, I mean, I guess it's got to be imaginary. It's a bit of a bummer because you always try to avoid speaking of complex numbers, but I think that's the way it is. So let me, I was going a bit ahead of myself. So let's look at this function more closely. Like I said at the beginning, so we want this to be true at yeah, excuse me, I'm just checking that I didn't get anything wrong. So we want it to be true at any point in space. Our medium in principle is unlimited. We have no boundary constraints yet, and at any point in time, maybe time larger than 0. Maybe we don't care about, well, no, we want to be valid at any time. So now if x becomes very large, this guy will explode unless lambda is negative or imaginary. So lambda cannot be larger, real and positive for sure. But then here I have a negative sign, and I know that v is, well, let's decide that v is positive just as a convention. So then this means that lambda also cannot be real and negative, and so we are left with lambda cannot be real and lambda has to be imaginary. Okay, so let's see what that means, and then I think I have to leave you, and we will discuss this again on Friday. But if lambda is imaginary, it means that, you know, like you might or might not remember complex numbers. You might or might not know about complex numbers. So you might need a little bit of reading of your math textbooks in the next couple of days. But let me, you know, we don't use imaginary number a lot anyway. So let me just quickly show what happens next. If lambda is imaginary, it means that we can write it as the imaginary unit times alpha, where alpha again is an arbitrary number, but now at least alpha is real. Or let's call it k. It's kind of more common. Okay, lambda is equal to I times some k. All the arbitrarity that was in lambda is now transferred to k, but we know that I has to be there. It's got to be the imaginary unit. And so then this becomes exponential. Let me compact this a bit, of lambda times x minus vt equals exponential of I k x minus vt. And now those of you who have worked with complex number before know that this is the same as writing cosine of k x minus vt.
Yeah.
E sine k x minus vt. I'm going to stop here because it's getting late. But I see you